All right, so I'm going to do an example of project part three. So this is the one where we're using the Tully-Fisher relationship. All right, so let's go over a couple of these things. 1 parsec is approximately 3.1 times 10 to the 16th meters. We need that conversion. The luminosity of our sun is approximately 4 times 10 to the 26th watts. And of course the inverse square law, right? The flux is equal to, I think the last video I called this a B, it doesn't really matter. Anyhow, the flux is equal to the luminosity of the object, whatever it happens to be, divided by 4 pi times the distance to the object squared. All right, so let's get into this. All right, so this example is for the galaxy Triangulum, which is actually called M33. It is a spiral galaxy. It's actually in the same direction as Andromeda, the one that we're actually going to use. So we're going to use the Tully-Fisher relationship, and we're going to find the distance in kiloparsecs. Okay, so that's the key there. And I'd like you to do that also with the one for Andromeda. Okay, so just follow these steps and you'll be fine. All right, so you first have to know. Oh, I guess I didn't spell that right. The rotation velocity of this particular galaxy, and so I just looked this up. It turns out to be 180 kilometers per second. All right. So just to remind you what that is, it comes from the broadening of the spectral lines. But basically, you get some spectral lines shifted to the red. That's of course the parts of the spiral that are moving away from us, and then the parts that are moving towards us, it shifts to the blue. And the overall effect is to widen the absorption line. All right. So we also need to know some more information about. So this is about Triangulum, right? So the rotation velocity 180 kilometers per second. The apparent brightness, or what we receive in our telescopes, is approximately 1.76 times 10 to the minus 10th watts per square meter. That's literally the amount of energy per square meter that we receive in our telescopes. So what we have to do, of course, is we take the inverse square law. The flux is the luminosity divided by 4 pi times d squared. So rearrange that and solve for d. And so the d comes over to the other side, and you just take the square root of the luminosity divided by 4 pi, also divided by the flux. All right, so that's it. That's what we have to do. What we also have to do is to figure out approximately what 180 kilometers per second is using this Tully-Fisher relationship. What I mean by that is we have to figure out what the luminosity of Triangulum is. Right? Remember, this is for the Triangulum galaxy. All right. So I'm going to just scroll up because I'm actually just using the same thing that you guys are using. All right, so there's the Tully-Fisher relationship. Notice it's not, we don't have a lot of data on these axes, so we have to use an approximation, which is exactly what we want you guys to do. All right, so there's 100 kilometers per second, there's 300 kilometers per second, right in the middle would be 200, so it would be slightly to the left of that, right? So I'm just going to move it a little bit to the left. I'm moving my cursor, and then of course for the Tully-Fisher relationship we go straight up. All right, so I'm trying, it'd probably be better to print this out and use a ruler. Okay, so yeah, roughly right here. And then once you get to that line, remember there's a relationship between the absolute luminosity of this spiral galaxy and the rotational rate. Okay, so then I go directly over, and so notice where I am. Right, I'm in between 10 to the 8th and 10 to the and oops, hold on, let's see. So this is so that's right here. So we go straight. So I think I didn't go quite straight up. So I'll go straight up and see. I'm actually a little bit further, and so I go over, and so in between these. So I'm a little above this. Okay, I'm above the halfway point is what I mean. So if I'm above the halfway point would be 10 to the ninth, right? And so I'm above that. I'm going to assume I'm halfway. So you know, between the 10 to the ninth and the 10 to the 10th. So I'm going to assume, and again, this is you know, speculative here, of course, because we don't have you know, a fine detail on this graph. So with that, I'm going to choose some number between 10 to the ninth and 10 to the 10th. So I'm just going to eyeball it and say, when I eyeball it, it's approximately halfway between the middle of this and the 10 to the 10th. So let's say it's 5 times 10 to the ninth. All right, that's what you need. All right, so let's go to another screen. All right, so from the Tully-Fisher relationship, which I, you know, looking at what the velocity was, the rotational velocity, I'm choosing to say that this was 5 billion, basically 5 times 10 to the ninth, times the luminosity of the sun. Remember that vertical axis is the luminosity of the sun. The horizontal axis is the rotational velocity. So this is what it is, right? 5 times 10 to the ninth times the luminosity of our sun, which is this 4 times 10. Whoops, that's a times. I don't know what I just did. 4 times 10 to the 26th watts. All right, so that's down here, and of course we were given the flux of 1.76 times 10 to the minus 10th. Notice the watts cancel. This is also in watts. This right here is also in watts. So the watts cancel, and you get 1 over meters squared, but then you're taking, so it flips the meters squared, so that comes up to the numerator. Anyhow, this comes out to be approximately 3, what did I get? 3 times 10 to the 22nd. 3 times 10 to the 22nd. 10 to the, that's a 10, sorry, 10 to the 22nd. And the answer is in meters. All right, so we still need to change this from meters to, where's my scroll? I gotta scroll down just a little bit. All right, there we go. And so, so this is 3 times 10 to the 20, so this is our distance, and we want to turn that into kiloparsecs. So I say, okay, well, 3 times 10 to the 22nd meters. And so I just say, well, okay, I know that in 1 parsec, there are, let's see, what is it? It's, oh yeah, 3.1 times 10 to the 16th meters. 10 to the 16th meters, all right? And so the meters cancel, as they should, and so that will give us the answer in parsecs, which, remember, we're going to want, so it's here, let me write the number out. So I'm going to write it up here. So it's going to be 970, and then it's a 045 parsecs, right? Parsecs, that's a 5. And of course, we want it in kiloparsecs, so if I move remember the decimal is after the 5, so if I move the decimal 3 places to the left, this is approximately 970, I don't know what I just did, 970 kiloparsecs. All right, so that's the distance to Triangulum. Okay, here, let's pause this. All right, so I'm going to take this even further and do this, what is this, second problem with you, but for the triangulum relationship, okay? So for that particular relationship, let's see, do I have it right here? I thought I wrote it down. Hold on, let me see if I can find it. Okay, I think I just wrote it down over here on this. All right, so anyhow, just like our project, we're going to choose within the galaxy, right? So this is within triangulum. We find a Cepheid variable, and this particular Cepheid, it's a type 2 Cepheid variable, so we got to use the correct graph, and I'll show you that in just a second. So the period is 30 days. All right, so let's look at that. Let's look at the this is the graph, and this is exactly the same graph that you have for this project. So we look here. Here's 30 days, and notice it's a type 2 Cepheid. There's the type 1 Cepheids. Anyhow, so the type 2 Cepheid, you just go up to this line. Okay, so we go straight up, and then we're going to go over. All right, so notice it's between 10 to the third and 10 to the fourth, right? So it's almost exactly midway between the two. So I'm going to say it's 5 times 10 to the third, right? Because if you divided this into, 10 equal chunks, it would be a halfway. So that would be 5 times 10 to the third. All right, that's the important part. From the period luminosity relationship. Which is exactly what project the last project was about. We can measure the distance using a Cepheid variable. All right, so we just found the distance using the Tully-Fisher method. So this is actually a good point. Is anytime you can, you want to get some kind of overlap, right? If you can actually make out a Cepheid variable within that galaxy, then you can check on the Tully-Fisher method. Did that actually measure things to the correct distance? All right. So from the graph, this is what I get. All right. So the luminosity on the absolute scale is 5,000 times the luminosity of the sun. So if we and the other thing that you needed to know is from that particular Cepheid variable, in my telescope, the flux that I receive is 1.76 times 10 to the minus 16th watts per square meter. Remember, this is just one single star. All right, so the energy is a lot smaller. Anyhow, it's the exact same equation, the inverse square law. So it's going to be the square root of 5 times 10 to the third, right? 5,000 times the luminosity of the sun divided by 4 pi, and then divided by this flux that was given to us. So when we do that, we get 3 times 10 to the 22nd meters, and so we just need to convert that to parsecs. And so let's just go ahead and do that. Here, I'm scroll up. Oops, didn't mean to do that. All right, so for parsecs, we know that in 1 parsec, 1 PC, that's supposed to be a PC. There are well, I don't really have room right here. I'm going to put this over here. In 1 parsec, there are 3.1 times 10 to the 16th meters, right? And so that's 16, and so the meters cancel, and you get again, it's a really large number. Here, let me yeah, it's not, so I'll put this answer right here. So this is D970, and then there's like three more zeros after that for meters, or for parsecs. So it would be like there's other numbers right there, but they're not really that important. So that's parsecs, and then of course to convert it to kiloparsecs, you move the decimal place 3 places to the left, and so this again turns out to be 970 kiloparsecs, right? 970 kiloparsecs. All right, so that is the example. You're going to do the exact same thing, but now you're using the numbers that are given to you for Andromeda. All right, so please work this problem, and yeah.